So good afternoon. First of all, I'd like to thank the organizers for hosting this wonderful meeting in such nice fashion for the last decade. So today I'm going to talk about conceptualizing a microscale engine that is powered by motor protein. And this work is done in collaboration with Suraj Deshmukh, Shiv Prasad Patil, Basudha Roy, Shogoto Guho, and Arnab Shah. So we are all familiar with a macroscopic heat engine, which operates between temperature bath and in the process extracts heat and converts it into work output of the system. And how it is operationalized is that you confine centimeter cube of gas and between fixed wall and piston, and then you are able to extract work. And of course, for these macroscopic systems, the fluctuations of the work that our usual laws of thermodynamics describe well the system, and the thermal fluctuations are relatively unimportant. Now, how does one realize a microscale engine? Okay, the system dimension, you scale it down to micrometers of the size of micrometers, and the typical energy scales are of the order of kBt, so that the fluctuations are important. Now, the experimental realization of such microscale engine was done in the seminal experiment by Blicke and Beschinger. So essentially what they did was they took a single colloidal particle, micron-sized particle, and that was subjected to a time-dependent optical trap potential, which was periodically coupled to two heat bath. So the working substance here is this micron-sized bead particle, which was in this optical trap, and the harmonic trapping potential has this form, and then you have this work output. And what they managed to do was to generate the analog of like a Stirling cycle, where you have two isotherms connected with this isochoric process. And here, in terms of thermodynamic variable, the analog is that the trap stiffness, which was varied, was like the generalized coordinate, a generalized displacement, and basically they managed to do this. Now, question is that what kind of work output do you generate in this fashion? And these are sort of the typical numbers that they got, that the average work, of course, it is a fluctuating quantity, but the average work, sort of the maximum average work that they could extract was of the order of less than kBt. And I should say that the constrained by whatever are the typical trapping potentials, it worked for a range of 10 to the power minus 4 piconewton, and the trap stiffness was varied between 10 to the power minus 4 piconewtons and 10 to the power minus 3 piconewtons, while the temperature of the bath was between 20 degrees and 70 degrees Celsius. And for those parameters, this was sort of the kind of numbers that you got. So of course, it is nice that you can actually have such microscale engine, but from a practical point of view, if you have an engine which is where the work output per cycle is of the order of kBt, in fact less than kBt, it would be very difficult to extract any meaningful work or make it work as a device. And so the question is, how do we improve the performance of a microscale engine? Can we harness the activity of motor proteins for driving a such microscale engine? So what we have in mind is a work-to-work converter at microscale. And the second point that I want to emphasize is that can information of the state of the system, and in this case, I'll argue that depending on the state of the system of the motor, whether it can improve the performance by an effective feedback control mechanism. So what is the system I have in mind? You again have this kind of optical trap setup, a micron-sized bead, which is connected to these motor proteins in an ATP-rich environment. So these motor proteins hydrolyze ATP, and they are able to walk on this underlying microtubule filament. These motor proteins have two binding domains, one which is irreversibly attached to this bead, and one which can stochastically attach and detach to this underlying microtubule filament. And when it is in attached state, it walks and drags this bead along. And so this would be the corresponding Langevin equation for the bead in the overdamped regime, where this bead would experience a force due to the trap, and the motor are also modeled as an effective spring. The important aspect that I would like to highlight is that here, of course, we have three intrinsic time scale: the thermal relaxation time scale, the hydrodynamic relaxation time scale of the bead to the trap center, and the time scales of this motor binding unbinding process. The important point to realize is that there is a clear separation of time scales of the motor unbinding process and the hydrodynamic relaxation. So what is the engine cycle we have in mind, which is feedback control? So you imagine that at the starting point, you have this bead and this motor attaches to the trap center. And then, so that's, let's say, happens at x equal to 0. And then you have this protocol that moment it attaches, the trap stiffness is changed linearly from some value k0. And until it walks certain distance, and then stochastically, of course, the motor detaches, and the moment it detaches, you instantaneously change the trap stiffness down to k0, and then finally, of course, the cargo will finally relax to the trap center, and that sort of completes one complete cycle, and one can calculate what is the work that is done. So these are sort of the three processes, and one can find out what is the the expression for the work output in one complete cycle. But remember, this is a stochastic quantity in the sense the binding and unbinding times are stochastic events. One can find out what is the probability distribution of this runtime of this motors, and there is an effective time scale which is dependent on the intrinsic motor velocity and the stall force of these motors. One can find out actually certain limits, like when this time scales are small, one can find out an expression of this average work that can be extracted in terms of these motor parameters. V0 is the velocity, epsilon naught are the unbinding rates. More generally, in general, if we look at the system, what we find, we actually look for this kinesin and kinesin 3 motors, and the kind of work output, the average work output that you get is at least 10 kBT or more. And these are the corresponding contour plots in terms of the trap stiffness and the motor velocities, which can be tuned in an experiment. And these are also the other indicators of engine performance, what is the power output of these motors. The broad thing is that even the kind of power that you can extract is 5 to 7 kBT per second. And so how does it compare with other microscale engines, including the engine that I just described? Like, you can clearly see that even other realizations of this kind of microscopic engines, which relied on extracting heat to work, generated at max, even with active baths, generated of the order of 3 kBT, and clearly the proposed engine has a performance capability which exceeds very well, and most importantly, it's much larger than the thermal fluctuations, so which makes it amenable of a practical device which can actually operate at microscopic scales and extract work at that scales. So with that, I would like to conclude my talk. So what we have shown is propose a blueprint for a microscopic engine, which is like a work-to-work converter, and the work output is at least higher by one order of magnitude than other micro engines, and importantly, one order of magnitude higher than thermal fluctuations. And the functionality of this engine is actually achieved due to this feedback protocol that I described and the separation of time scales that I illustrated. And the fidelity of this engine is controlled by the stochasticity of the unbinding process of the motor and not by the thermal fluctuations like for these other micro engines that have been devised. So thank you for your attention, and I'd like to stop.
So you were studying the efficiency of this engine, and the protocol you were quenching with linear protocol. So can it be changed if you introduce some other protocol?
Yes, see, meaning here we have just considered a linear simple protocol, but in principle you can play around with the kind of protocol you would devise.
I'm asking in terms of expediting the efficiency.
Probably yes. We have not investigated in details how the efficiency can be even optimized. Even here, how I have defined efficiency is just mechanical efficiency in terms of what is the. So here, it is like a work-to-work converter. So essentially, the work done by motor is converted into the work output of the engine, and part of it is thrown to the heat reservoir at whatever temperature. So yes, in principle, it can be optimized and increased. Yes.
Thank you. Thank you.
So, Sudipto, one question here.
Yes.
Things are a bit unclear to me. So, just wanted to have some clarification. So we know that power output of any motor protein is fixed, which is decided by its design. Okay,
Yes.
right?
Correct.
So I don't understand why you are calling it as an engine, and the role of the increasing the trap stiffness linearly is unclear to me. I mean, what it is
So
doing.
first point, that's why I said it's a work to work. The engine, the motor, you can think of it, it's generating some power, it's doing some work. In fact, if you go back to, we had plotted, for instance, what is the typical average work that is done by the motor on the system. So the system here is the beat. So that's the kind of work, it will have certain power. You are having a system which is able to utilize that work input from that motor and convert it into the work output of the system. That's the answer to your first question. And your second question was that, no, meaning it is not that even if you, like I said, that there's nothing sacrosanct about linear increase. It is just that, you could have increased it even with certain protocol. The important step was in overall work extraction, because you want the system to do work, then that instantaneous step is actually crucial. One point which I didn't touch upon because of shortage of time was that you can question that, for a practical experiment, the feedback control, I am sort of saying that the feedback control, it's sort of the system that means that the motor is in bound state or unbound state. But typically, if you do any optical trap experiment, there is actually a feedback delay when the time that will be required and in that sense, if the feedback delay is too long, this engine will stop performing. You will not be able to extract work. But we also calculated that for typical numbers of the feedback delay, so as long as the feedback delay is less than the hydrodynamic relaxation times, and which can easily typically be achieved for this IR laser type experiments that one does, then this engine will be able to function. And here I have described only for one motor. This proposal can be generalized to utilizing working with even multiple motors. Only thing is that the fidelity of this engine in that case will go down, but the work output per cycle will improve.
Okay, so let's thank speaker again.
Thank you.